In continuing on our discussion of the convergence rate of conjugate gradient, I'd like to recall the bound we have on the energy norm of the current iterate, xk, with the exact solution according to the A norm. The bound that was given here, it's important to realize that there is a significant difference between the bound in conjugate gradient and steepest descent, is that in this particular bound, this quantity that's raised to the little k power here is the square root of k minus 1 over the square root of k plus 1. And of course, you could reduce that to just the factor 1 minus 2 over the square root of k plus 1. Capital K, this is capital K now, which is the condition over the matrix. For steepest descent, that factor inside that's raised to the k power is 1 minus 2 over k plus 1. So you see a significant difference between the value of k here and the square root of k. The square root of k divided into 2 is going to provide a much larger number to subtract from 1, meaning this will drop significantly less than 1 for conjugate gradient, whereas it may not with steepest descent. So that's an important difference, is to realize that square root of the condition number is key here, not just the factor that's a 2 out there. So, and also to point out that, again, it's the condition number, which is the ratio of the largest to the smallest eigenvalue. I notice sometimes in Bjork, he seems to have this backwards, lambda n over lambda 1, maybe misinterpreting. The first one is usually the largest to the ratio to the smallest. So this error bound typically describes convergence for matrices having what are referred to as uniformly distributed eigenvalues. So in other words, when they're uniformly distributed, this is typically the convergence rate you would get. Now you can do things, which we're going to talk about in just a minute, to change the iteration matrix so that perhaps that the conditioning will be causing an effect where, that the eigenvalue distribution will change so that the convergence rate actually would improve. But this is not making any assumptions here. This is just assuming the eigenvalues are uniformly separated, and that's about the convergence rate you would expect from conjugate gradient, which is certainly better than the rate for steepest descent. So Axelson did a lot of work, and he was in the Netherlands, and did a lot of work in the modern history of these iterative methods such as conjugate gradient, and he showed that conjugate gradient usually converges in 3 phases. In other words, according to 3 different kinds of scenarios. One is the convergence will be affected by your initial vector. The closer you are to the original solution, typically you're going to converge faster. So your initial guess x0 and subsequently the residual corresponding to it give you the fact that R0 is just B minus times A x0. That is significant. Typically, the convergence is linear with the rate depending upon the spectral condition number, capital K. But sometimes the convergence is what's referred to as superlinear, and it takes much less than n iterations for an n by n matrix, say. So sometimes the convergence is exceedingly good, and it has a lot to do with the spectrum of the original matrix. So these are 3 different scenarios that contribute to the convergence of the conjugate gradient method. So that leads us to this next topic, and the final topic we're going to talk about with iterative methods, which is the idea of preconditioned iterative methods. So we'll talk about preconditioning as a general technique for improving iterative methods, and then finish up by focusing specifically on conjugate gradient. The rate of convergence usually depends in iterative methods on the eigenvalue distributions and the initial residual vector. The goal of a preconditioned system solved iteratively is to improve the convergence rate by preconditioning your system, which means in this case multiplying essentially a matrix, an inverted matrix, P inverse AX equals C, where C now is P inverse B. So you've taken AX equals B, and you've essentially multiplied it on the left in this case by P inverse. So you've maintained the original solution X, but now you're trying to solve a system where essentially the coefficient matrix now is of this form. This is called left preconditioning because you've multiplied on the left of the original system. The improvement in the convergence for these methods usually occurs, as indicated here in my notes here, the improvement usually occurs if that preconditioner, that P inverse times A, is essentially almost becoming the identity, right? So it almost acts like the inverse of the matrix A. It won't be exactly, so we're not expecting it to be equal here. But the closer it acts like its inverse, the better off it will be in speeding up the convergence. More importantly, if the eigenvalues of this matrix, P inverse times A, P is the preconditioner, if those eigenvalues of that matrix are tightly clustered away from the origin, you will get a great improvement in your convergence rate. The worst case is what is based on the bound we showed before, where they're uniformly distributed, they're all separated. But if you can produce a preconditioned system where you have clusters of eigenvalues very close to each other, you're typically going to get a faster convergence. So, the mechanics of the preconditioner, again, you want, if you're thinking of norms, the norm of A minus P to be small. You want P to act very much similarly to your matrix A. But more importantly, in some extent, from the cost per iteration, you want the ability to solve with that preconditioned matrix to be very, very easy. Very easy to solve systems of the form PU equals V, where P is the preconditioner. If you had a right preconditioned system, you would be multiplying on the on the right with P inverse rather than on the left. And you would end up solving this system, A P inverse Y equals B, where then Y would have to be P times X. Because you could see, then you would have A P inverse P, which would be the identity, times X. So that's A times X equals B. So this is the system you would be solving. Typically, the spectra of whether you precondition on the left or the right are the same, but there is a slight advantage sometimes for preconditioning on the right, and that is you would still be able to estimate the residual of the original system pretty well, because if you think about preconditioning on the right, again, the solution that you're seeking, X, is just P inverse Y, or Y equals just P times X. So as you're producing this P inverse Y, as you're solving and getting Y, you're immediately you're able to get the residual. Okay, so it's just one slight advantage of this configuration with using multiplication on the right. But whether you choose to precondition on the left or the right explicitly, you would never ever form these matrices, never. So you typically are generating them indirectly with the use of matrix vector products. And I'll illustrate that with the original MATLAB code that we had for conjugate gradient in just a second. So again, P inverse is never explicitly formed. You typically are just solving a system. Perhaps the preconditioner is diagonal. Perhaps it's triangular. It needs to be something easy to work with, right? But you're never going to form its inverse explicitly. So one approach, in theory, that tends to work pretty well, and let me scoot this down a bit, for producing optimal preconditioners has to do with splitting. So one approach is to find your optimal preconditioner by looking at a splitting of your matrix into two components, A1 and A2. So suppose we split A as A1 and A2. You really want, let's say, A1 to be very easy to solve with, perhaps triangular, perhaps diagonal. And then you would choose that preconditioner to be the A1 block, or the A1 matrix, excuse me. And hopefully what's left over in A2 would have very low rank. In other words, most of the independence has been captured and there's just a little bit left. But it would have very low rank in the A2 block. So let's finish out with a section on specifically applying this technique of preconditioning to the conjugate gradient algorithm, right? So this is 4.4.1 in the Bjork book. And what we're looking at is a technique called PCG, or Preconditioned Conjugate Gradient. So here, what we're looking for is a preconditioner n by n. We're looking for it to be Hermitian and positive definite. So we're typically using conjugate gradient on a Hermitian positive definite system, or a symmetric positive definite if you're in the reals. And one thing you can do is choose your preconditioner to be a Cholesky factorization, perhaps, because it is a HPD matrix. We can always produce a Cholesky factor of it. So such a split preconditioned system would be something like this, that if you have your preconditioner and you have its Cholesky factors, you could precondition on the left and the right, on the left by L inverse and on the right by L inverse Hermitian. Okay? And you would be solving this perturbed system here, where a LHX is this X tilde and LB tilde is equal to B, where X and B are the original solution and the original right-hand side. That's called a split preconditioned system. And then what you do is in each preconditioned conjugate gradient step, you would have to be able to multiply by this L inverse A, L inverse H, P, where P is your current direction. You'd have to be able to scale by this. You'd have to multiply by this system times P. So again, you never form these terms, these inverses explicitly. So it's sort of a three-step approach. Take your current direction vector, solve LH, call it P hat, which essentially gets you the L inverse P part. Then form Z equals A times that P hat, right? And then finally, to accomplish that left precondition, you would solve L Q equals Z. And therefore, you will essentially have computed L inverse A, L inverse H, P. The rate of convergence typically depends on the spectrum of the preconditioned systems. And here's the goal. You could get a rapid improvement, faster convergence, if the condition number of this split preconditioned system is smaller, and or that this new system P inverse A has only a few distinct eigenvalues, which means you're getting some tight clusters. If it has very few distinct eigenvalues, that is ideal for improving the convergence rate. So finally, let's look at some common preconditioners, and then we'll go back and look at that Matlab code to see how you would actually do preconditioning inside of the conjugate gradient algorithm. So recall the standard splitting that we were using when we were building iterative methods, taking a matrix, writing in the form D minus E minus F. D is diagonal, E and F are the strict lower and upper triangular components of the matrix. If you went back and looked at your notes on stationary iterative methods, remember the iteration matrix would be looking at of some form in inverse N, which could be written as I minus inverse A, where you've done the original splitting A equals N minus N, and of course B is the iteration matrix. You can actually think in terms of preconditioning for Jacobi method that the preconditioner is just simply the diagonal matrix, whereas the preconditioner in the Gauss-Seidel method is just D minus E, right? But in terms of conjugate gradient in general, choices for preconditioners, it depends on, again, it's a cost issue of how much you're going to increase the cost per iteration versus the amount of acceleration of convergence you're going to get. That's the ultimate trade-off, and we'll summarize that in just a second. But the simplest preconditioner is to choose the diagonal, which is simply gets a diagonal scaling of the rows of A. If your matrix is symmetric positive definite, you could use split preconditioners with L and LH and square root of D would be one possibility. And let them all, you could simply use the square root of the diagonal matrix as the L and the LH that we had earlier. That would be a very simple way of achieving diagonal scaling. But what's very common, what's related to your homework problem in this section is what are called incomplete factorization methods. Incomplete LU and incomplete Cholesky are very common preconditioners used in system solving by conjugate gradient. I'll talk just briefly about ILU, which is incomplete LU. The idea is to compute a lower triangular matrix L and upper triangular matrix U that have the same sparsity structure as A. It's not the complete LU because you don't really worry about the exact values. You're just trying to estimate LU by having a similar sparsity structure of A. It'd be almost like if you were doing Gauss elimination and throwing away any element, not allowing any fill into the factors if that element wasn't in the original matrix A. And that's why it's called incomplete LU. So you would have maybe had the original L and U, but when you drop out the values corresponding to entries of the original matrix, which didn't exist, you've kind of put holes in L and U. But you still want to have L times U in terms of this incompleteness, still kind of close to the original matrix A. This is a wonderful technique that's effective for elliptic PDEs, and if you go on to do a lot of research or taking courses in PDEs, ILU preconditioners are very common. You typically are working within matrices and diagonally dominant matrices, and because they're diagonally dominant, you can drop out values in the factorization and still have a lot of the essential effect, the commonality of the original matrix A in terms of its structure and even its spectrum. Some implementations of ILU and incomplete Cholesky use a drop tolerance. Again, you have to have the strategy to decide when you're going to drop values. So some elements one strategy is to use this tau drop tolerance, which is usually not greater than 0. And you'll create or store elements only if their absolute value is greater than that. And it's typically small, somewhere between maybe 10 to the minus 4 and 10 to the minus 2. That would be a very large drop tolerance. So again, when values fall less than this tau value, you don't keep them. Right? So again, the ultimate trade-off with the preconditioning techniques, especially conjugate gradient, is you want to improve the convergence rate, but you don't significantly want to increase the cost per iteration. So that's the trade-off. So what I'm going to do now is go back to the original MATLAB code that we had. Let's go back to the MATLAB code for conjugate gradient, and what we're going to do is look at how a preconditioned conjugate gradient code would be different. So if you remember in your notes, we had this original function called CG, which is Matlab-style function here. And what I'm doing here in blue is indicating how a preconditioned conjugate gradient, just like if we were to insert a little p here, how would a preconditioned system work? Right? So I've only indicated the lines of the code that would change. For example, originally you would choose your first direction to be the residual. Now, because of the preconditioned system, P would be M inverse R, where M is the preconditioner. Or, again, you don't explicitly solve the system. You don't explicitly compute the inverse. You would solve this system. Maybe it's diagonal scaling. Maybe it's a triangular solve. But again, it's very cheap. The alpha parameter would change in terms of the computation we did here in the original CG method. Here you would have a sequence where you would again have to solve a preconditioned system with the residual being the right-hand side, the current residual. Once you've solved it, D, you would set vector, say D, which would be R transpose times C. And then having that, you could then produce the new alpha value directly. It would just be D divided by P transpose times Q. A little bit later on with beta, similarly, you would have to solve a preconditioned system here, MF equals R with the new residual, set G equals R transpose F, and then update your beta that way as the value, the scalar G divided by D, because G and D are both scalars. And then you would update your direction vector, having that F available to you from solving the original precon system here with the new residual. And so the new direction vector is updated this way. So this just illustrates how the code changes if you have preconditioning. IACCG, which is incomplete Cholesky, CG is this technique where the preconditioner again is Hermitian, in this case symmetric positive definite itself, but the L here is what we call an incomplete Cholesky factor. It would be doing the same Cholesky procedure we normally would do to factor a symmetric positive definite matrix, but this L is going to be much sparser because you don't allow any fill. You cannot put any values into this L matrix that don't correspond to non-zeros in the original A. So there can be no fill. So that's why some people call it a no-fill factorization. Has the same, so the L matrix here has the same non-zero pattern as the lower triangular part of A. And the same thing for L transpose, because of course A is symmetric, so that makes sense. So that's how incomplete Cholesky would work. In this case, the M matrix being L transpose, the product of those two. And you would have to solve up here, you would be solving LL transpose inverse times R, and then here you're doing LL transpose F equals R there. So that is sort of a nice little illustration of how conjugate gradient becomes preconditioned conjugate gradient with an incomplete Cholesky factorization.